Hello.
How are you guys feeling?
How are you, Mr. Poole?
You know, motivation level is okay. You know,
It's all right.
been worse.
Yeah.
How about our seniors here? How is your relative motivation level? Through the roof and negative. Love it. All right. I have some good news for you guys. You guys have passed the point of things that I should be brand new to you. We're now entering into the phase of like we're going to do some stuff that you did already in Algebra 2 or should have done already in Algebra 2 with a little bit more or less, to some extent, depth to things. So here we go. You guys ready? We're going to Algebra 2 it up. Sound good? All right. So today we're going to do 13.1 and 13.2. In 13.1, we're just talking about graphs of polynomials. I'm not going to ask you to generate any graphs by hand, but there are some key features from the graphs of polynomials that we'd want to be able to identify. So I'm just going to kind of describe what these things are visually. You okay, Hacky? Okay. So these 3 points where the graph crosses the x-axis are x-intercepts, or oftentimes we'll refer to those as zeros, or they might be referred to as roots for the polynomial, or even you might call them solutions. So far, so good. Okay. So these points are the extrema. There's 4 types of extrema. There's local minimum, local maximum, absolute or global minimum, and then absolute or global maximum. So this one that I've highlighted in blue, what type is that? Do you remember? It is a local maximum. Excellent. So if we look in just like the general region around it, it's the tallest point in that region. But if I expand it to a bigger area, it's not necessarily the tallest point possible. Everybody okay there? And then the other extrema here would be like a local minimum, right? Is everybody okay with those ideas? Remember that from last year, talking about extrema? Is there any good way to find those extrema algebraically? Not without calculus. How would we do it in practice in this class? With our graphing calculator. We'll review how to do that here in a few minutes. But that's going to be the way that you'll find those extrema in this class. And then you have the ends of our graph, which is the end behavior. So we're going to use a specific notation for end behaviors in this class. I'm going to translate it into English and then show you how you write it symbolically, because I think that's just kind of the easiest way to approach it. So the four cases, you can have the left arrow pointing down. That's what's happening here. That left arrow can point up. The right arrow can point down, or the right arrow can point up. For polynomials, these are the four possibilities. You're going to have two for every polynomial function, one for the left and one for the right. So now I'm going to write symbolically how we're going to write these things. Oops. Great googly moogly. That's an oopsie. So the way you read that symbolically, you say the limit, that's the LIM part, as x approaches infinity, or negative infinity, that's the part underneath the limit, of f of x is, that's equals, and then you'd say again, positive or negative infinity. So the left part is the negative infinity there. The down part is the negative sign there. The up part is the positive sign there. And then I need one more color. I'll do pink. And then right is the positive. So this is just like some definitions, right? And a little bit of notation. So far, so good?
Yeah.
Okay. So let's do a little rundown with the calculator. So if you have your calculator with you, I invite you to take it out to follow along. If you prefer to just sit and watch and do it later, that's okay too, no big deal. If you need to borrow one, I have calculators sitting on my desk. You're welcome to grab one and borrow one. That's what they're there for. Make sure I get it back, though. All right, so this example asks us to do two things. It says to locate the zeros and then the extrema. I'm going to use my calculator to do all of this. So to do this on my calculator, I'm going to start by entering this function into the y equals. So I'm going to press the y equals button in the upper left. I have a bunch of stuff in here. I'm just going to clear that stuff out. If you have anything in there, go ahead and clear it out. So the only thing in there is going to be what we're going to type in right now. X cubed minus x okay. Now, most of us have been using our calculator to do the stuff in the last chapter where we would probably have been making scatter plots and all that kind of hooey where we've been using zoom stat. Who knows what our window is set to right now? So rather than resetting it to something manually, I'm just going to do zoom standard. That's just going to reset my window to the sensible -10 to +10. So there's my picture. Now, it's a little bit tough for me to see everything I'm interested in. The zeros and extrema look like they're happening right in this section, right? You guys see that? So I'm going to look a little bit closer there. You could do this two ways. You could zoom in or you could reset your window manually. I don't think the calculator zoom usually works very well for me. I like to reset my window manually. But you could choose the zoom in option there and center it at the origin. You'll probably be fine. So if I look at this, it looks like everything I'm interested in happens between, say, -3 and +3, and between like -2 and +2 on the y. You guys agree with that? So I'm going to go to my window, and I'm going to reset the x min and x max to like -3 and +3. I'm going to leave that scale alone. And I'm going to set the y mins from -2 to +2. Again, I'm going to leave everything else the way it is. And then I'm going to hit graph again. That's a better picture, right? Can definitely see what's going on there. So if I look, how many zeros do you guys see? 3. 1, 2, 3. To find those, I'm going to press second and the trace button. And I'm going to select, surprisingly, the 0 command. Now, if I look at the bottom of my screen, the calculator is asking me a question. So it's asking me for a left bound. So I need to pick which 0 I want to find. Let's say I'm going to find this one first. So the left bound, I need to tell my calculator some point to the left of that 0. So I'm just going to, I see my cursor here flashing in the middle of the screen. I'm going to use the left arrow to move that cursor over so it's on the left side of that 0. So that looks good there. I'll press enter. Now the question has changed. It's now asking me for a right bound. So I'm going to go ahead and move my cursor to the right. That looks good. Press enter. It asks for a guess. The guess doesn't matter as long as there's only one 0 in between your left bound and right bound. So I just always just press enter again. So my first 0 is -1, 0. That's what the calculator's output for me. See how it says 0? And it tells me the point. Everybody's good? Try to do the next 2 on your own. Yes, you may.
Is it so?
Wait, what'd you do once you plug in the thing? How do you go from there?
Press graph.
You mean invalid convention?
It's because you still have a plot on with no data in it, probably. So press the y equals up at the top where it says plot 1, 2, and 3.
Yeah.
Unhighlight everything that's highlighted there. Just press enter.
Oh.
And then try hitting graph again.
There we go.
Okay. You go second trace and pick the 0 command. Oh, unless you need to zoom. Find the extrema. Second trace. What do you think I want to use here? If I'm looking for the extrema. The extrema are mins and maxes, right? So I'm going to use the minimum command to find a minimum and the maximum command to find the maximum if they exist. So let's do the minimum first. I saw that it has both of them. So the minimum looks like it's right here. Everybody agree with that? The calculator is going to ask me the same 3 questions as it did with the 0 command, a left bound, a right bound, and a guess. So I'm just going to move my cursor to the left of where I think that minimum is. Press enter. I'll move it to the right of where I think that minimum is. Press enter. And the guess, I just press enter again. So my local minimum is at 0.577 comma negative 0.385. And then my other is this spot right here. That's a local maximum. So I'll do second and trace. I'll pick the maximum command. One too many. The calculator is going to ask me the same 3 questions, excuse me. I'm going to move my cursor for a left bound. That looks good. I'll move my cursor for a right bound. That looks good. The guess is fine where it's at. And there's my other one, which is negative 0.577 comma positive 0.385. Mm-hmm. How do you guys feel about using the calculator to do this? You should be comfortable doing that. That's something I would definitely ask you to do on like a quiz or a test, is be able to use your calculator to find, zeros or extrema. Okay? Don't be surprised at that. Now, what would be nice is if we had an idea of how many of these things I should be looking for, right? Like finding them once, not so bad, but sometimes I'm going to have 3 zeros. Sometimes I might have 1 0 or 2 zeros or 2 extrema, 3 extrema, 4 extrema. How do I know how many I should be looking for? Well, this theorem here that we're giving gives us an upper bound on the number of zeros and the number of extrema that we can have. So it says a polynomial of degree n. Remember, what's the degree? It's the biggest exponent. Will I have at most n zeros and then n minus 1 extrema? So let's do a quick example to kind of show you how we can use that. Okay, for the function y equals, or f of x equals 3x to the fourth minus 5x cubed plus 2x plus 2. How many zeros could there be? How many extrema could there be? I'm going to start by calculating the degree. What is the degree for this polynomial? Four, that is correct. Again, just the biggest exponent. So the number of zeros is going to be at most 4, the same as the degree. If you do not write the words at most, I am going to not give you full credit. If I ask how many zeros could there be and you say 4, that's wrong. What does at most 4 really mean?
Or it could be 1, 2, 3, or 4.
Yeah, you could write. We don't know how many there's going to be, but I know there can't be more than 4. But there could be 3 only, there could be 2, there could be 1, there could be 0. Any of those are in play. So either you write out all the possibilities or you have to include the words at most. Okay, I'm not going to remind you again. What's the number for the extrema? Is it 3 only? What word should I include before that? At most 3. 1 less than the degree. So again, you could write that as 3 or 2 or 1 or 0. Or you could just write the 2 words at most. I'm going to write the 2 words at most. When I do that, does this feel okay? Pretty easy theorem to use. Does it tell me at all how to find these things? Nope. Doesn't give me any help on doing that, other than, if I found 4 of them, I found all of them that I can find for the zeros. Or if I find 3 of them, I know I found all I can find for the extrema. But if I find only 2 zeros, do I know I found them all? Not necessarily. So this is a little bit incomplete, right? We'd love to know, like, when we're done, when I know that I found them all. But that's coming later. Do one more example here right quick. So I'm going to ask you to write the end behavior here. So let's write this end behavior first. If you describe that end behavior, is that the left end or the right end? That's the left. Is it pointing up or down? Up. So I want left arrow pointing up. That's this one. So I'm going to write the limit as x approaches negative infinity of f of x equals positive infinity. Is everybody okay with how I'm doing that? So I'm just looking at my picture and then translating it into the symbols. Is that the left arrow or right arrow? Right. Is it pointing up or down? Up. So I want the right arrow pointing up. That's this one. So I'll write the limit as x approaches positive infinity of f of x equals positive infinity. So again, I'm just going to copy it down. And I'm done, right? It's just like, do you know the notation and the definition? That's it. What do you guys think? Super okay? Try to keep it as simple as possible, right? All right. Next up, that's it for section 1. Yes. So this next section is going to be about finding the zeros of polynomial functions algebraically, i.e. we're going to be using factoring. So I'm just going to recall for you guys some important factoring techniques that you would have studied last year in your Algebra 2 class. So there's the difference of two squares. I abbreviate that as dots. There's the sum of two cubes, or the difference of two cubes. Oops. You guys remember these factoring patterns from last year? There is factoring trinomials that are in the quadratic type, where the leading coefficient is 1. Or where the leading coefficient is not 1. And then there was grouping. I think would have been like the 5 major well, I guess we should probably have. And then like a greatest common factor. Would have been like the 5, or well, I guess that's 6 factoring techniques that you guys would have studied last year. What I like to do when I introduce this, or when I teach this, is I build like a flow chart that kind of dictates what techniques are going to use given the different circumstances, and then we'll go through and do some examples of stuff in a minute. So I'm going to build out that flow chart for you guys right now. Oh, that's embarrassing. I'm just going to say. So the first thing we're going to do is look for a greatest common factor. And then from there, after I've factored out my greatest common factor, if there is one, what I do next is dependent on the number of terms in my polynomial, whether it's binomial, trinomial, or quadnomial. I don't know what a four term, if there's a nice term for that. Okay. If it's 4 terms, what we try is factor by grouping. If the answer is, if we can do that, we factor by grouping, and then we go to the 2-term branch to check that for each of my factors. If it's no, then we stop. There's nothing more to do. Yes. Yes.
Wait, so a term is like a number and a variable?
So like x squared plus 2 is 2 terms. X squared plus 2x plus 5 is 3 terms. X cubed plus 2x squared plus 3x plus 7 is 4 terms. Okay. If I have 3 terms, I ask, is it in the quadratic form? Yep. If it's not, we stop. There's nothing to do. If it is in that quadratic form, then we need to check to see if the leading coefficient is equal to 1. If the answer is yes, we can do the shortcut. If the answer is no, you have to do the long way. We'll review what those mean in a second. If the shortcut works, then you have to check your factors that you're left with. If the shortcut doesn't work, then you're stuck. There's nothing more to do. You have to stop. Same thing with the long way. If the long way works, then you have to check each of your factors down the 2-term branch. If the long way doesn't work, then you stop. There's nothing left to do. And then if it's 2 terms, so the first thing you're going to check if it's 2 terms, is it a difference of 2 squares? If it's yes, you have to factor it, and then you have to check each factor down the two-term branch. If it's no, then you have to check, is it a sum of two cubes or a difference of two cubes? If that's yes, then again you have to go down that two-term branch. If it's no, then you stop. There's nothing more to do. So this, I crammed together in there, got a little squished at the end, is my flow chart for algebraic factoring. So let's do some examples here of how, and use the flow chart kind of as we go, so I can show you guys how this is kind of, how this functions. Okay. All right. Yes. Sure. Okay. So we start out at, the first step is to set the thing equal to 0. Then we're going to check for a greatest common factor. If I look at x cubed minus 6x squared minus 8x equal to 0, is there anything in common with all three terms? An x. So I'll factor that out front. Okay. Now I'm going to look at the remaining stuff and look at the number of terms. How many terms do I have? 3. So are those 3 terms in that quadratic form? I mean, not much. Yes, it is. Right? Because the degree of the first term is twice the degree of the second term, and the third term is a constant. Right? If I look at the exponents, it's 2, 1, and then no variable. So that's good. Okay, so we're yes. Is the leading coefficient 1? Yes. Oh, what happened there? So we can use the shortcut here. So what I'm going to ask myself is, what 2 numbers multiply to give me -8, and then add to give me -6? Well, that's not right, because those don't add to get, or don't multiply to give us -8. But that probably should have been a positive. That's just a mistake in the book. So let's just do that. And now -4 and -2 work. Is everybody okay there? That's the short way, where you don't have to do any factor by grouping anything. All you have to do is answer that question. So that worked. We did it. Now we have to check each of these 2 factors down the two-term branch. Is x minus 4 a difference of 2 squares? No, because the first term is just x, not x squared, right? Okay. Is it a sum or difference of 2 cubes? No. Well, the first term is just x. It's not x cubed. So we're done with that one. For x minus 2, is it a difference of 2 squares? No. Is it a sum or difference of 2 cubes? No. So we're done with that one. So this is fully factored. Now I'll apply the zero product property, where I'll take each of these factors and set that equal to 0, and then solve. So x equals 0 is a solution. X equals 4 is a solution. And then x equals 2 is a solution. So my zeros would be like 0, 0, 4, 0, and 2, 0. Does that feel okay there? Did you guys see how I'm using that flow chart? It's pretty helpful, right? Let's do a Mr. Kulik example. Oops. I guess we should say like f of x equals. Okay, f of x equals 2x to the 6th minus 128. So we'll start again. Greatest common factor. Is there anything in common between 2x to the 6th and 128? 2. Great. So I can take out a greatest common factor of 2. I'll set that equal to 0. Okay. Oops. What's the number of terms? 2 terms. Okay. Is it a difference of 2 squares? Yes, it is. Why did you say no? But 6 is an even number, right? So couldn't I think about it, x to the 6th as x cubed squared? Anytime you have an even degree, that's going to plant you squarely in the difference of 2 cubes, or 2 squares possibility. Is 64 a perfect square? Yeah, right? That's 8 squared. So that does factor into x cubed minus 8 and x cubed plus 8. Everybody okay there? Okay, so we did that. And now we have to go back to the 2 terms branch and check each one of those. So is x cubed minus 8 a difference of 2 squares? No. Is it a sum or difference of 2 cubes? It is. Is it the sum or is it the difference? It's a difference. Yeah, because of the subtraction there. Hopefully you recognized 8 as 2 cubed. And then obviously the other one is going to be a sum, right? You guys see that? So if I apply my difference of 2 cubes factoring pattern, I got that. I use those guys that we gave you at the beginning. Okay. All right, so we did yes and yes. So now we have to check these guys to see if those are factorable still. Are either those a sum of or difference of 2 squares? X minus 2 and x plus 2? No. Are they a sum or difference of 2 cubes? So this is done. Our factoring is finished. So I'm going to take each factor and set it equal to 0. What do you guys think about this flow chart? Is this nice?
Yeah.
Especially for like these more complicated problems where there's kind of a lot to do. It's pretty helpful. Okay, 2 equals 0. Well, that's stupid. That has no solution to it. That's a bunch of nonsense. X equals 2. X equals negative 2. How am I going to try to solve these guys? You'd have to use the quadratic formula. So, but better than that, that trinomial part of a sum or difference of two cubes always has imaginary solution to it. So if it has an imaginary solution, can it be a x-intercept? No, man. It can't. So it can't be a 0. So even though it's a solution, it's not one we care about. So guess what I do with it? I just ignore it. I'm just going to write NRS underneath them. What do you think that stands for?
No real.
Excellent. No real solution. How do we feel here? Is this okay? What we're doing? Remind you of stuff you did last year, I think. Bella's like, oh dear God, yes. Okay. I have one other definition that I want to talk about here. And then one more example. So that I can probably zoom in a bunch now and like stop using the giantest pen. So that definition is multiplicity. So let's say we have x squared plus 6x plus 9 equal to 0. How does that factor? Again, multiplies for 9 and then adds to 6. X plus 3 and x plus 3, right? That's good. So again, we can use our zero product property to set each of those equal to 0. And we solve, and we get x equals negative 3 and x equals negative 3. How many solutions did I get?
2.
I really got one solution, right? But I got the same solution more than one time. So we'd say that that solution, x equals negative 3, has a multiplicity of 2 because it occurred 2 times. If I'd gotten the answer 3 times, I would say it has a multiplicity of 3, and so on and so forth. Does that feel okay? Now, the nice part about these multiplicities is that they have a graphical analog. So if I think about the graph of Yep. So let's say I have some graph of f of x and it has some 0 at x equals a. Depending on how that 0 occurs, I can tell the multiplicity of that 0 just by looking at the picture. This first situation is called a straight, because I notice the graph passes straight through the x-axis. That 0 is going to have a multiplicity of 1. You okay, Grace?
Yeah, I just need to clean it.
Oh, yeah, I got some on there. The second situation is called a bounce. There, the multiplicity is like an even number, like 2, 4, 6. We don't know how many times it's going to be used, but it's going to be used an even number of times. Or that solution is going to occur an even number of times. Do you see why we're calling it a bounce? Because it looks like it hits the x-axis and bounces up off of it. And the last one is called a bend. And here the multiplicity is 2k plus 1. It's going to be an odd, but it has to be bigger than 1. So to have multiplicity 3 or 5 or 7. With a little greater than 1. Okay? So this will become helpful for us later on when we start dealing with polynomials that are not factorable using that factor flow chart that we just built, but are still factorable using other methods. So when we play Sherlock Holmes a little bit later on, this will become really a helpful clue to us. Did you guys do this last year in Algebra 2? Talk about multiplicities and bend, bounces, and straights? Does that sound familiar? Okay. All right. I have one more example, and then I am done for today. That was not too bad, I hope. All right. So this type of problem is called an optimization problem because it's asking us to find the best way of doing something or the optimum solution. The problem says a company wants to create a cardboard box with an open top. You guys can picture what that means. You've had like where you have to pull the lid off something and the box left over is like, okay. The box needs to have a volume of 500 cubic inches and is created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. The piece of cardboard is 26 by 20. What size squares should be cut from each corner in order to create the proper volume? So what it's talking about is it's going to let's use a different color. Oh, come on, computer. What is the lag for here? Is we're going to like cut the corners out so that when we fold up, we make our box. Can you guys visualize how that's happening? Okay. That was 26 inches. So we're asking, the question asks, what size of squares? So I'm going to call that side length for my square x. That's what we're going to be solving for. Okay. So we're told that volume that we need is 500 cubic inches, right? Who remembers the volume formula for a box from your geometry class? Very good. Length times width times height. Okay, so what I'm going to do now is I'm going to go to my diagram that I've drawn and figure out which sides are, or which spots are the length, the width, and the height. So when I fold my box up, I'm going to be folding along that plane, right? Or that line. That would be like my length. Everybody agree with that? And then I'll fold along this line. That'd be like my width. And that means that like that line would be like my height. Everybody feel okay picturing how this is going to fold up in 3 dimensions? Sometimes that's challenging. You feel okay? My job now is going to be to rewrite my length, my width, and my height in terms of x. One of them is very easy. Which is the easy one? I would say the height is the easiest one. What's the height in terms of x? I mean, just x, right? Just the side length of that square. The square has all side lengths x. Everybody agree with that? Okay. What's the length going to be? Well, I know the whole box is 26 long, right? But what have we cut out from it? We've cut that and that. So it should be 26 minus 2x. What's the width going to be? Very good. So the equation that we're going to be looking to solve for then, I know the volume needs to be 500, and that's going to be length in terms of x, width in terms of x, times height in terms of x. Does everybody feel good there? Now to solve this, I mean, if I really wanted to do it, I'd have to FOIL this thing out, subtract the 500 over, and then run through that factoring tree, hoping that it's actually something factorable, right? I don't want to do that. That sounds like a lot of work and something where I'm not guaranteed to be able to do the problem anyway, right? Like if the problem is just a cuckoo decimal with like a radical in it, maybe I won't even be able to find it. Because that's going to be a degree 3 polynomial, right? So instead, what am I going to do? I'm going to solve this by graphing. So I'm going to graph one side of this equation in y1, and I'm going to graph the other side of the equation in y2, and I'm going to find the intersection. Okay, before I do that though, I want to think about some sensible values so I can pick my window. What is the biggest possible value for x? Obviously x could be 0, but what's the biggest possible value for x here? Take a look at the equation, see if you can see it. It's 10. Because if x is any bigger than 10, that term is going to become negative, which I know we can't have a negative width, right? Everybody can kind of see that. So you can just use if it's a geometry problem, you can just make sure that you're not getting a negative side length. Okay. So that's going to be all I really need to get pick a decent window for my on my calculator. So I'll go in here, and inside of Y1, I'm going to type 500. And inside of Y2, I'm just going to type this exactly like it looks on my sheet of paper. I'm not going to FOIL that out because, woof, that looks like a lot of work. I'm not going to try to get everything onto one side because, again, that looks like it might be kind of a lot of work. I'm just going to leave it the way it is. Now that I've got this entered, I'm going to go to my window. My x's are going to be between 0 and 10. I know that guarantees the side lengths of this box are always positive valued. I should say non-negative. Now let's think about our y's. The y is going to be, it needs to at least cover 500, right? So I'm going to pick a little bit below 500 and a little bit above 500, maybe like 250 to 750 or something. As long as I can see y equals 500, though, I should be good to go. I'm going to hit graph. There's my line for y equals 500. There's my volume function. I see I get two solutions out of this. Let's find this one first. So I'll do second trace, and then I'm going to pick the intersect command. The calculator is going to ask me 3 questions. It's going to ask me first curve, second curve, guess. Well, I only have 2 things graph, so first curve, second curve, I just press enter on each of those. For the guess, though, since I have 2 crossings, I have to be careful. I'm going to move my cursor so that it's close to one of them. So it finds that one first. So one answer is 1.20. So I'll go and find the other one now. So I go back, intersect command, first curve, second curve, just press enter on each of those. And then for my guess, I gotta move over by that other intersection that I'm looking for. And 7.02. That was the first intersection I found. That one over there.
Oh.
How do you guys feel? Is that okay? Nothing too crazy there today. So you guys should be able to do now 1 through 15. Most of that, though, is pretty straightforward. Oh, I guess I didn't do this. One other thing. Okay. I forgot to do one other thing. Here, I'm actually just going to... -5, -1/2. And I forgot them now. What is it? 5, -1/2. This is like number 13 from the homework. So this is basically going backwards from factoring. Yes. Sure. Sorry, I lied about being done. So we know that since it's 0, or those are zeros, that this polynomial has the solutions 5, 8, and -1/2, right? I can like subtract 5 from both sides of the first one. I can subtract 8 from both sides of the second one. Add 1/2 to both sides of the third one to get that. I don't love this fraction over here, though. So what I'm going to do is I'm going to just multiply both sides by 2 so that I don't have a fraction to deal with. So now if I multiply these 3 binomials together, since they all equal 0, the product of all 3 of them is going to be 0, right? So this polynomial I've just made has its degree 3 because it has 3 x's that we're multiplying together. And the solutions are going to be 5, 8, and -1/2. So all I have to do is FOIL this out, and I'm done. So let's do that real quick. So I'm just going to FOIL the first 2. And I'm just going to do that kind of quickly in my head. Again, if you can't do that in your head, no big deal. Write it out, more steps if you need to. And then to FOIL a 3 and a 2, I'm just going to kind of do that kind of thing. And then if I just combine my like terms, that's the cubic polynomial I'm looking for. Again, if you haven't seen that done before, maybe it's not obvious how to do that, how to back engineer something. But that's all you need to do is just turn each solution into a polynomial, multiply all those things together, FOIL it out, and you're donezos. Now I'm done for realzos. So you guys should be able to do 1 through 15 from the problem set. And I also have a delta math built for you guys. That delta math is going to be doing the factoring stuff using the flow, using the flow chart that we just made. There's kind of a lot of them. We'll take time in class on the X day to work on that also. So I'm going to give you some time to do it in class as well. Okay?
Thank you.
Mm-hmm.